students, now we will study about optics. Optics has two mainly branches. One is ray optics, another one is wave optics. Before that, let us understand what is meant by optics. Optics is a study of light and its phenomena. Right? In case of what is optics is also a branch of physics which deals with the study of light and its phenomena. And at the same time, in this session, we are going to learn about ray optics. The ray optics mainly contains the propagation of light in a straight way, and or in the corpuscular way, in the form of particles, right? But there is a clear difference between ray optics and wave optics. In case of ray optics, we consider that light travels in a straight path. But whereas in the case of wave optics, we consider that light travels in a wave form. Right? In these phenomena, the many scientists work, namely Kepler, Newton, and Corpusculus, and Galileo, Copernicus. All their work in this aspects, and their contribution is very important in this research, mainly even Newton also. Right? After this, let us see that what are the things we are going to learn in this chapter. In this chapter, we are going to learn about reflection of light and the reflection of light by spherical mirror, and the reflection of light, refraction of light we are going to learn. Then laws of refraction and principle of reversibility of light. Then refraction through glass slab or parallel slab, or even instead of any slab of a different refractive index. Then refraction through compound slabs, and the apparent depth of the liquid we are going to learn, and a total internal reflection. This is a very important aspects. Many phenomena we are going to discuss based on this. Then refraction of spherical surfaces by sign convention, and by considering some sign conventions, and the refraction at convex and concave surfaces. Then after that, we are going to derive an equation of a lens maker formula. Then after that, we are going to learn about a lens equation, and we are going to learn about linear magnification. Then refraction through prism, expression of refractive index by prism, then dispersion of light, then after that dispersion and dispersive power of the angular dispersion and dispersive power, then blue color of sky and red color of sun in the morning and evening, then compound microscope, then astronomical telescope, then astrometric telescope, but a reflecting type. That is mainly it is called as a Cassegrain reflecting type telescope. Right, anyway, let us understand first and foremost phenomena that sometimes we call it as the ABCD of optics, that is reflection of light. What is meant by reflection of light? It is very simple thing is that when a light is incident on a surface and it come back, right? So a bouncing back of light on same medium after striking a surface is called as reflection of light. Means when a light falls on a surface and after that it come back, no? That whatever let us forget about the direction it is moving, right? But when it falls on a surface and comes back, this phenomenon itself is called as what? A reflection of light, right? Important thing is that the laws of reflection. So there are two laws of reflection we come across. Already you might have studied in class 10th and even in lower classes also. Let us see that once again here what are that, right? So here you can see this. this is the incident ray. This is incident ray. So when a light ray is incident on this surface, right, after that it will reflected like in this manner, right. At the same time, here is a normal. Normal is an imaginary line drawn on the surface, right. So therefore, when a light ray is incident on a reflecting surface, then it will reflected back in the same medium. But on the basis of that, we come across two laws. First one is this. This is angle of incidence, where this angle of incidence is the angle between incident ray and normal. So this is usually denoted by I, right. Then another one angle is the angle between the reflected ray and normal. It is denoted by angle R, right. So therefore here the angle I and angle R, right, angle I and angle R are equal. It means that angle of incidence and angle of refraction are equal, right. So therefore that is why we call it as angle I is equal to angle R, right. So therefore that's what. So first law we say that the angle of reflection is equal to the angle of incidence. In the same way we come across another second law, that is the incident ray, this is incident ray, and the reflected ray and normal, right, all lie on the same plane. It means that the plane, all these rays are lie on the same plane. It means that, for example, you see here, suppose if a light ray travel, it come like this and it is reflected back like this, and if you draw a normal here, the incident ray, the normal and reflected ray all lie on this plane. You can see a plane here, right. So therefore, so many times it is not like that all the three lights are standing on this one. No, wrong. So there is a misconception in your minds. So conception is very simple. Light, this ray and reflected ray, then this is normal. All these are in this same plane, right. This is what we are going to learn, right. So this second law states that the incident ray, reflected ray and normal to the reflecting surface at the point of incidence all lie on the same plane, right. So after this, when you go for this reflection through mirrors or curved surfaces, then we need some sign conventions. The sign conventions is very simple, right. First one is, that is all the measurements should be, let me take it here, all the measurements should be measured from the pole of the mirror. So here you can see, right. So this is, right, all the measurements should be measured from the pole of the mirror, right. First sign convention. The second sign convention is the distances measured in the direction of incident ray, in this direction, right, are taken as positive. So distances measured in this direction all should be taken as positive. The distances measured opposite to the direction of incident ray, means in this direction, if you are measuring, it should be taken as negative. So therefore, one thing please remember, if you measure the measurement from in this direction from this pole, and if you measure the measurements measured from this pole in this direction, they should be taken as negative. This should be taken as negative, this should be taken as positive, right. So this is the second convention. That's what we will come across here. The distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. Then after this, another convention is that the distances measured above the principal axis, this one, the distances measured above the principal axis are taken as positive, distances measured below the principal axis are taken as negative. Distances measured below the principal axis are taken as negative. This is positive, right. So these are the conventions required for any further understanding of reflection by surfaces, concave and convex surfaces. After this, let us go for focal length of a spherical mirror, right. So before that, we must understand what is meant by principal focus in case of concave mirror and convex mirror as well as, right? In case of uh, if you take a parallel beam of light rays incident on the reflecting surface of a concave mirror. See here, you can see this. So this one. So this surface here, just in this side, what we have taken is the polished surface. This is called as polished surface, and this one here you can see this is called as a reflecting surface, right? So therefore, when a light ray travel like this, right, parallel to principal axis or parallel incident on the reflecting surface, all will converge at single point. All will converge at a single point. This point of convergence is called as principal focus. In the same way, if a parallel beam of light rod incident on the convex mirror like this, if you incident on the convex mirror, right, they will be reflected back in such a way that they appear to be come from the single point. This point of divergence, the point of divergence is called as a principal focus of a concave mirror, right? At the same time, here one more terms we come across here, it is C. So this C is called as what is center of curvature. Center of curvature, before going to center of curvature, if you take the curvature or the reflecting surface of this mirror, it is a part of this is a part of a sphere. This is a part of a sphere, right? So if it is, since it is a part of a sphere, obviously it must have a center, right? So that center is called as a center of curvature, right? And at the same time, here the distance between principal focus and pole of the mirror, distance between principal focus and pole of the mirror is called as a focal length, and distance between center of curvature and principal pole of the mirror is called as a radius of curvature. So similarly in here also, in case of concave mirror, convex mirror, that is the distance between pole and C, the center of curvature, is called as a radius of curvature, and distance between pole and F, principal focus, is called as a focal length. It's called as focal length, like this, right? It is usually denoted by F and R, right? So that's what you come across here. Now let us understand the relation between the focal length and radius of curvature of a concave and convex mirror, right? So that is, now let us consider a figure here. You see here a light ray parallel to principal axis is passing like this and incident on the reflecting surface. Then after that it will passing through the principal focus, right? So this is, and one more line we draw from C to M, right? This is angle of incidence you can consider, because it is the angle between the surface and the radius of curvature is 90 degree. This is 90 degree. Right? If this is theta, obviously this must be theta, right? And you see that this line and this line, principal axis. So these two are parallel. If these two are parallel, we consider this is these two angles must be equal, because alternate interior angles. So if this is theta and this is theta, this is theta and this is theta, then obviously total angle is 2 theta. This must be 2 theta. Right? Angle MFD or MFP is equal to 2 theta. Then if this is theta and this is 2 theta, by using the property of property of exterior angle, we can see that if this is theta and this must, the sum of these two angles must be theta, 2 theta. So therefore this angle must be theta. So based on this, let us take here, right, angle MCP. Angle MCP is equal to angle M, and angle MCP, let's take here. Angle MCP is equal to theta, and angle MFP is equal to 2 theta. MCP is theta and angle MFP is 2 theta. Okay, so therefore from figure and by using tan theta we will write tan theta is equal to MD by and CD. MD by CD because opposite by adjacent, and tan 2 theta is equal to MD by FD we will write it. Right? So therefore theta is equal to, for small angles we can write theta is equal to MD by CD, and here 2 theta is equal to MD by FD. MD by FD will take it. So in place, the same thing we can write it as 2 into, in place of theta we can write MD by CD. MD by CD we can write it, that is equal to MD by FD we can write it, right? And here we cancel this MD and MD, we will write it as 2 by CD is equal to 1 by FD, right? We will take the reciprocal of this, CD by 2 is equal to FD. Then what CD, what is CD? It is capital R. R by 2 is equal to, what is FD? FD is nearly equal to F. So therefore R by 2 is equal to F. In this way we can take it. Otherwise we can follow this in systematic manner and we can do it. That is for angle theta, and MD by FD is equal to 2 MD by CD. We take it here and substitute here, right? Then you cancel this MD and MD, then you will get FD is equal to CD by 2, and FD is equal to F because FD is nearly equal to F and CD is nearly equal to R, capital R. So from this we understand that the focal length is equal to half of the radius, otherwise radius of curvature is equal to 2 times focal length, right? So this we have learnt in class 10th, but we didn't know the derivations, right? So from this slide we understood that how the relation is obtained. Okay, now let us go for another topic here, that is path of light rays. This you have learnt it already, but let us discuss once again, right? So if a light ray is incident parallel to principal axis, right? So if you keep an object somewhere else, then if a light ray is incident parallel to principal axis, then it will be reflected back and it will passes through principal focus. It will passes through principal focus. Then if another light ray is obtained from the same object, but if it is incident on the pole of the mirror, and here it follows the laws of reflection. Angle of incidence is equal to angle of refraction. Then another light ray, if it is passing through center of curvature. So, but whenever light ray passing through center of curvature, it is incidenting on the reflecting surface perpendicular to this. So therefore, it will retrace back and moves in the same path. And in another way, if a light ray is passing through principal focus, suppose here it is not run, here if a light ray is passing through principal focus, then after reflection it go like this, parallel to principal axis, right? Because here otherwise if light ray is taken here, by using the property of reversibility, we can find here light ray go like this, passing the principal focus, then it will reflect back. Okay, right, now let us understand the mirror formula of concave or convex mirror, right? So mirror formula already you know that in the previous class you have learnt in class 10th, that is 1 by f is equal to 1 by v is equal to 1 by u, where f and u are, f, u and v are focal length, object distance and image distance, right? But there just simply have learnt it and as it taking it as a granted. But whereas here in this class in the 12th we are going to have derivation, and this derivation may be asked in the examination. Many times it is asked in the examination also. right? Let us see that how it is obtained, right? That is, now let us keep object AB far away from the center of curvature, right? When you keep an object far away from the center of curvature, where the image forms, obviously it is between the center of curvature and principal focus. So that is what we can see here. So image formed between A and B, right? So then we can also prove that here triangle A dash B dash F is similar to triangle MPF. Okay. So we can prove that. How we can prove it? Just we'll see that here. Now these two angles, this angle and this angle, are equal because vertically opposite angles. Now, and this angle, that is angle A dash B dash F, and this angle MPF, are perpendicular. Even if you do not agree, what we do is we consider a line here like this and we can take it. Okay, and this distance is very small because we consider a small aperture. Then once these two angles are equal, obviously third angle must be equal, and hence these two triangles are similar. So once you prove that these two triangles are similar, that is what A dash B dash F and triangle MPF, then corresponding ratios of sides are equal. So that is here B dash F must be equal to FP, and A dash B dash by MP is equal to B dash F by FP. A dash B dash by MP is equal to B dash by B dash F by FP, right? Then is in place of MP we can write AB here. In place of MP we write AB because height of AB is same as height of MP. We'll write it. We'll call this equation number 1. Then after that, similarly we consider another triangle here. Triangle, this one, A dash B dash P, this one, is similar to triangle ABP. How? Let us take here. These two angles are equal. Okay, these two angles are equal, and this angle is 90 degree and this angle is 90 degree. If these two angles of this triangle are equal, and obviously third angle is equal, hence these two triangles are similar, or AA property. By using AA property, you can say that these two triangles are similar. Triangle ABP and triangle A dash B dash P, right? Then obviously the ratio of the corresponding sides are also equal. The ratio of the corresponding sides here, A dash B dash by AB is equal to B dash P by BP. We'll take it. That's what we'll take here. A dash B dash by AB is equal to B dash P by BP. Right? Then let us call this equation number 2. Let us call this equation number 2. Right? Once then from equation 1 and 2 you compare here. The left hand sides are equal. That is A dash B dash by AB and A dash B dash by AB. If left hand sides are equal, the right hand sides must be equal. So therefore, we can say that B dash F by PF is equal to B dash P by BP. That's what we write here, right? So then one more thing here, B dash F you see here, B dash F. Right? Actually, remaining all things are you can put in terms of U and F, U, F and V. But whereas except B dash F, this is right. So here what we'll do is instead of writing B dash F, we take B dash P minus FP. We'll take it. That's what we write here. B dash P minus F, otherwise P B dash minus PF. By same remaining things are same. PF is equal to B dash P by BP. We'll take it. Then using this sign convention, we should write these terms in terms of U, V and F. U, V and F. And all these measurements are in the left hand side, that is opposite to the direction of incident ray. So you see here incident ray is going like this, and you are supposed to measure all the measurements from pole, right? So, and you are measuring in this direction, so therefore all the measurements should be taken as negative. So then therefore, so wherever in place of BP, BP, we can write it as V, right? V, that to minus V. Then in place of minus PF, we can write it as F, that to minus F. Then in place of same PF, once again minus F you write it. Then B dash P, this is image distance, that is minus V by BP, this is BP, object distance U, you write it here. Then in the next case, what do you write in both separate terms? That is minus V by minus F, right? That will be V by F. Then the minus of minus plus by minus F. So that will be minus 1, you will get it. That is equal to, here minus get cancelled, V by U get it. Then multiply throughout by 1 by V, we get 1 by F is equal to minus 1 by V is equal to 1 by U. Then take this minus 1 by U to other side, then we can write it as 1 by F is equal to 1 by U plus 1 by V. So that's what we'll take it, right? So this is what the mirror formula is, right? After this, let us go for magnification. What is meant by magnification? Magnification is the ratio of the height of the image to the height of the object. So that will come across, that is, we write it as M is equal to H dash by H. That is the definition, we will take it. That is M is equal to H dash by H, right? H dash by H. So from the previous figure itself, we can once again we consider this same triangle A dash B dash P, A dash B dash P, and ABP here, right? So therefore, let us take the heights here now. That is A dash B dash by AB is equal to B dash P by BP. That is it. So then A dash B dash is equal to A dash B dash by AB is equal to B dash P by BP. That's what we'll take here once again. Okay, B dash A dash by BA is equal to B dash P by BP, right? Then, but here we'll come across the sign convention. That is AB is taken as positive, and A dash B dash will be taken as negative, right? So therefore, here we will take it as H dash minus H dash by H, H dash by H actually, right here, because it is taken in the numerator. H dash by minus H is equal to minus B by minus U. So therefore, H dash by H is equal to minus B by U, will take it, because this minus get cancelled, whereas this minus will be taken to other side. So that we will write here. So then we write this magnification H dash by H is equal to minus B by U. Now let us go for another important phenomena, that is the refraction of light. Refraction of light, and you have come across this in previous classes. It is when a light travels from one medium to another medium, it changes its path. This phenomenon is called as what? A refraction of light. Right? For example, here when a light ray travels here, then it has to go in the same point. But instead of that, either it go like this or it go like this. Right? So this phenomenon is called as a refraction of light. It can also be defined in another way also. That is, it is when a light travels from one medium to another medium, it changes its speed. Either it may increase or it may decrease. Right? So let us see this. After this, there are laws of refraction. As like in laws of reflection, here also two laws of refraction. The first law is this: it is as same as the reflection. That is, right, when a light ray incident on the interface of the two medium, right, light ray is undergo refraction. The incident ray The refracted ray and normal drawn are in the same plane. Here you can see now. This is incident ray, this is refracted ray, okay, and normal. All are in the same plane. It means that suppose if you consider this is a light ray incident here and it go like this, then you would draw a normal you are drawing, then all these are in the same plane as like in the previous one. Then another law is the ratio of sine of angle of incidence to the sine of angle of refraction is constant for given pair of medium and for given color of light. Right? So that is that ratio is also obtained a constant. That constant is called as a refractive index. Later on we will study these things. So therefore, let us see this with some examples. For example, here if I draw, let us consider. Let us take here one interface of the two media. Then this is a normal. Then here you draw an angle here. Say about this is 30 degree. And it undergo refraction here. It undergo refraction like this. You get some angle. So if you take here sine 30 by sine of R1, let us take it. It is called R1. We got some value. In the same way, I will do one more thing. Here I will draw a normal here. Then instead of 30 degree, I will take here 45 degree. 45 degree let us take. And it bend like this. This is angle of refraction R2, let us take it. Then sine 45 by sine R2. That whatever the value you take R2, you keep it here. Then here let us take another angle. Instead of 45 degree, let us take 60 degree here. Then it undergo refraction. This is R3 is there. Sine 60 degree by sine, you will get some value, that is R3, let us take. Right. So if you take these values and substitute and you will get it, and you will get the same value. Suppose if you take it this, you got it as 1.47. This also will be 1.47. This also will be 1.47. So therefore, for any angle of incidence, if you take the ratio of corresponding incident, sine of the corresponding incident angle and sine of the corresponding refracted angle, the ratio will be constant. Here is 1.47, 1.47. But one thing, this is for given pair of medium. Suppose here you had used air and this is water. So here also air and water. Instead of that, if you use air and glass, then sir, is the constant remain same? No. Even for different angles, it will be ratios will be different. So that's what the says. It is same for given color of light and color 7 is given pair of medium. But at the same time, is it same for same color of light? No. If you use different colors, then this constant will be, suppose here you have used yellow color. What the light used is yellow. Here also use yellow. Here also use yellow and you get 1.47. Instead of using yellow color, if you use red color, then is it same? No, it will be different. But if you use for different angles, that will be same. Right? So in this way, we can understand the law here. Let me go back and we'll see this thing here. So therefore, that is the ratio of sine of angle of incidence to the sine of angle of refraction is constant for given pair of medium. Right? For a particular given pair of medium, it is constant for any angle of incidence, and for given color of light. If you change the color of light, even if you use the same pair of medium, it will be different. That is the meaning. Now let us understand what is meant by refractive index, how it is actually. The refractive index of a medium will be very different for different transparent medium, right? So one thing you should see that the optically denser, rarer medium has lower refractive index than the denser medium. Number one. Number two, denser medium with respect to rarer medium more than the rarer medium to denser medium. Right? It means that if refractive index of air with respect to water is different and refractive index of water with respect to air is different. Right? So that's what you will take it here. Suppose refractive index of water with respect to air is greater than refractive index of air with respect to water. That's what refractive index, the denser medium with respect to rarer medium. This is a denser medium with respect to rarer medium, and rarer medium to denser medium is smaller, right? And in refraction, the velocity and wavelength of the light are changed, right? So when a light ray travels from one medium to another medium, these two things will change. One is velocity, another one is wavelength. But at the same time, you must know that the frequency will not change. Frequency will not change. Right? So therefore, this also we are going to prove in next chapter. Then in refraction, frequency and phases of light will not change. So here, and one more thing. So refractive index of a medium with respect to air can be written as speed of light in air to the speed of light in medium. Then similarly, the refractive index of a medium with respect to air can be written wavelength of a light in air to the light in the medium. Right? So therefore, suppose if I write here, so mu W with respect to air is equal to VA by VW, right? And mu W with A is equal to lambda A by lambda W, wavelength of light in air to the wavelength of light in water, right? Similarly, here we can write it as glass, mu glass with respect to air, that is VA by VG. Similarly, in terms of wavelength also you can write it mu G by mu G with respect to air is equal to lambda A by lambda G. Now let us understand the principle of reversibility. Right? The principle of reversibility is that if a light ray incident passing in one direction and it undergo refraction or reflection. If a light ray travel in the opposite, if you keep a plane mirror which is perpendicular to the incident ray, it will retrace its back. You see here, light ray travel in this manner and it comes here. And if you keep this reflecting surface perpendicular, here angle should be 90 degree. This angle should be 90 degree. Then what will happen? It retrace back. It will go like this. This is called principle of reversibility. Right? Even not only that, suppose if you keep a mirror like this, a light ray incident here and it go like this. Okay. At the same time, if you pass a light ray here in this manner and it go like this, means here if you keep a reflecting surface perpendicular to this incident ray and it retrace back. Right? So therefore, here you can see that how it can be proved. So suppose if here you take a refractive index of B with respect to A. Refractive index of B with respect to A is equal to sin I by sin R. Then the refractive index of A with respect to B. Refractive index of A with respect to B is equal to sin R by sin A. So because one more thing you note that refractive index of A here. Refractive index of A, mu A with respect to B into mu B with respect to A is equal to 1 because they are reciprocal to each other, right? So therefore, by using that property here, mu A into mu B is equal to 1, then we can write like this, mu AB is equal to 1. Then here mu AB as it is I am writing here, right? And mu BA will write in the reciprocal here, okay? Then you see that what will get it. So if a ray of light after suffering any number of reflections and refraction has a path of reversed at any stage, it travels back to the source along the same path in the opposite direction, right? So after traveling through any number of refracting surfaces, then if you keep a mirror perpendicular to that is light ray which is obtained, then it will retrace back and go back to the same path. That's what called as a principle of reversibility. Then after this, we'll go understand the refraction through parallel slab or a glass slab. Let us take here a glass slab, right, of thickness T and a refractive index mu placed on a table, right. Then a light ray is incident here like that, which makes some angle theta, which angle angle of incidence I1, and undergo refraction. It is angle of refraction R1, and but the same light ray incident on the another interface here. This is another interface with the angle I2, right? After that it go like this, and this is called as incident ray. This is called as emergent ray, and this angle is called angle of incident, and this angle is called as angle of emergence. So therefore, and from this we can note that this incident ray and this emergent ray are parallel, right? We can prove it also. Let us take now here refractive index of B with respect to A. B means here it may be glass. B with respect to A can be written as sin I1 by sin R1, and we can write mu here. When here light travel from denser to rarer, that is maybe glass to air. So therefore refractive index of A means air with respect to this medium, that is B, can be written as sin I2 by R2. And one more thing you note here, this angle, angle R1 is equal to angle R2, because here these two are parallel. These interfaces are parallel. If these two are parallel, then these two normals drawn are also parallel. So therefore here this angle, if you consider these two angles, angle R1 and angle I2, angle R1 and I2 are alternate interior angles. So if these two are equal, then here if you multiply these two, mu B with respect to A and mu A with respect to B, you see that then I2, sin I2 and sin R1, they get cancel each other. Then we can write sin I1 by sin R2 is equal to 1. So if sin I1 by sin R1 is equal to 1, let me write here. So from this, sin I1 by sin R2 is equal to 1. So cross multiplying this, you will write it as sin I1 is equal to sin R2. So we can prove that I1 is equal to R2. What is I1? Angle of incidence. R2, angle of emergence. So therefore, from this we can prove that angle of incidence is equal to angle of emergence. So that is what here. So, but one thing is this. But there emergent ray is not going along the incident ray, but there is a shift in this one. So actually, in the absence of this glass slab or this medium, so it has shifted this. In the absence of this medium, the light ray should have gone like this, but because of this presence of this medium, it is shifted here. This shift is called as lateral shift. So this lateral shift is depend upon one thing, that is thickness of this. The thickness is not the breadth, it is a breadth. Thickness is breadth, not the height. Okay. So therefore, it is depend upon the width of the glass slab and angle of incidence I1. This one. If it more is the angle of incidence and more is the lateral shift will be there. Right. Here you can see that. For small angles, you can write the same equation like this. It is depend upon these quantities: angle width, and another one is I1, angle of incident. R1 is obviously R1 is depend upon I1, so we can mainly consider incident angle and width of the glass slab, like this. Then after this refraction through compound slab, means if there are number of slabs are there, right? Here, light ray travel from one air to one slab and to another slab and to air. Then it emerges. Then there is a lateral shift will take place regularly when it travel from one interface to another interface. When it travel through one interface to another interface. So it will be like this: I1, R1, where I1 is angle of incidence. This R1 is angle of refraction in first medium, and the same ray incident on the another interface here with an angle of incidence R1, because here R1 both are equal, as I told you in the previous slide. Here also same thing. So then after refraction through the another second medium glass slab, then it will be R2, here also R2, then it emerges out with them. But I1 is equal to I1. Emergent angle of incidence is equal to angle of emergence. So therefore, here you can write it mu B with respect to A in the first interface. Sin I1 by sin R2. Mu B with respect to C here in this interface. Mu C with respect to B. We write it as sin R1 by sin R2. Then in this interface, mu A with respect to C. That is equal to sin R2 by sin I1. So if you combining all this, if you multiply all these together, then what will happen? This R1 and this R1 get cancelled, and this R2 get cancelled. Then sin I1 and sin I1 also get cancelled. Ultimately is equal to 1, you will get it. So therefore, refractive index of A with respect to B into refractive index of C with respect to B and refractive index of A with respect to C is equal to 1. So if you take this A with respect to C, this is A with respect to the other side, you can get like this. You will get 1 by this. And take the reciprocal, then you will get the refractive index of C with respect to A. Refractive index of B with respect to A, same thing we are writing here. I will write here. Here. You can see that this is same, and C with respect to B, this is also same. Right? This one you are taking to the other side, right? That is mu A with respect to C in this manner. But if you take the reciprocal, then you can write it as mu C with respect to A. Mu C with respect to A, you can write it. Right? So therefore, refractive index of C with respect to B can be written as this manner. Refractive index of C with respect to A to the refractive index of B with respect to A. Now let us go for the apparent depth of the liquid, or we can find the refractive index of a liquid by finding the apparent depth of liquid. Now let us consider a coin inside water of a certain height HR, and here you see now, when you keep a coin below the depth of the bottom of a container, then it is appear to be raised up, right? Why it is appear to be raised up? Let us see. Because even not only that, you suppose sometimes in a lake or sometime there you see that the bottom is appear to be raised, but where real thing is that their depth is very long or more. Right? Now let us consider a coin at the bottom of a container. Then when you view from here, a light ray travel from in this manner, and it will go like this. So it go here. Let us see, in the presence of this medium, if you draw a in the objects of the medium, it would have gone like this, right? But it go like in this manner because of when light travel from denser medium to rarer medium, it go away from the normal. Right? It go away from this normal, it go in this manner. So when but at the same time, when you see from here, then it does appear to be come from this position. This appear to be come from this position. That is why the coin is appear to be at this position. Right? Let us see that how we can obtain the refractive index by finding this one. Okay. So refract now when the light travel from denser medium to rarer medium, means this medium water medium to air medium. So refractive index of second medium will be taken as mu A. So therefore, refractive index of A with respect to B can be written as sin A by sin R, right? So here, then mu B with respect to A can be written as sin R by sin I. So let me see here. I will take this. One more thing is this: refractive index of B with respect to A can be written as reciprocal of refractive index of A with respect to B. So therefore, that is equal to 1 by sin I by sin R. So that can be written as sin R by sin I in this way. So that is why refractive index of B with respect to A can be written as sin R by sin I. Okay. Then sin R by sin I can be written as, and this is by taking the opposite side is same, opposite by hypotenuse. And for small angles, you can take the corresponding sin R, corresponding sin I is proportional to tan I, and sin R is equal to tan I. By taking that proportionality, we can get HR by HIA, where HRI is real depth and HIA is apparent depth, right? Therefore, from this you can find out the refractive index of a medium, that is by knowing this real depth by apparent depth. Therefore, you can write here like this. You can note this one. Okay. So refractive index of a medium is equal to real depth by apparent depth. So therefore, apparent depth of a number of immersible liquid means if a number of liquids are there. For example, here instead of this, right, if there is another medium, say about kerosene is added here, and over that one more liquid is added over that, if it contain, if different liquids are added, then in that case apparent depth can be obtained by this. H is equal to sigma I is equal to 1 to n hi by mu I, like this. Then apparent shift means how much it is shifted. This is called shift here, that is HR minus HA. HR minus HA is apparent shift. So therefore, apparent shift can be obtained like this. HR minus HA is equal to HR minus HA can be written as HR by mu, like this. So therefore, HR, if you bring it out, then you can write it as 1 minus 1 by mu. Since mu is, by using this equation, mu is equal to HR by HA, like that. So whereas HA can be written as HR by mu here, then HR, if you bring it out, then you can take it out 1 minus 1 by mu, like this. So another important thing or interesting thing is this. So when you look from the top towards liquid, otherwise then it is appear to be raised up. At the same time, when a fish is looking from the bottom, then it is any object outside that water, it is appear to be farther from the real position, right? So as when you see from the top of the liquid, it is appear to be raised up, but whereas when you see from inside the liquid, the distance is appear to be farther what they appear, right? Right. After this, we'll go for total internal reflection. It is another fantastic phenomena, right? So this by using this concept, we can explain so many concepts, so many applications. So total internal reflection. So before that total internal reflection, the condition required for this concept is that the light has to travel from denser to rarer medium. Now let us consider this is air, right? This is a denser medium, glass or water, whatever you take it. Now let us take a light rays go and incident normal to the interface of these two, air and glass. Then it go vertically upwards like this. Then suppose if a light ray incident with some angle, say I1, then it undergo refraction, but it go away from the normal, it go like this. Suppose in the same manner, let the angle of incidence a little increases. We will increase this angle of incidence. You see here, this angle, say suppose this angle is I1, we call it. This angle is I2. So here I2 is equal to, is greater than I1. Is greater than I1. Okay. So now further we'll increase this one. But at particular angle, you can see that the angle, the refracted ray grazes the interface of the two medium. Here you can see it grazes the interface of the two medium. Right? This angle of incidence at this position, right? This angle of incidence is called as what? A critical angle. Critical angle. Right? So therefore, critical angle can be defined in this manner such that it is an angle of incidence when a light ray travels from denser to rarer medium. The refracted ray grazes the interface of the two medium. Right? Then after that, if the angle of incidence is more than critical angle, then what will happen? It undergo reflection into the same medium. This phenomenon is called as total internal reflection. Right? If angle of incidence is more than the critical angle, the light ray undergo reflection into the same medium. This phenomenon is called as a total internal reflection. Right? So therefore, the condition for total internal reflection are two. Number one, the light ray has to travel from denser medium to rarer medium. Number two, the angle of incidence must be greater than the critical angle. Right? Then only this is it will happen. Right? So then the incident ray must be optically denser, and the angle of incidence must be greater than critical angle. That's the relation between critical angle and refractive index. Now let us see here. We will have a relation between critical angle and refractive index. You see, so refractive index of air with respect to glass, mu A with respect to glass can be written as sin I by sin R. But sin IC, where what is angle of incidence? Sin I, critical angle, that is IC, will write it. Then angle of refraction is 90 degree, that is sin 90, will write it. So that is equal to mu, that is equal to sin IC, will write it. Right? So therefore, mu, refractive index of any medium, can be written as sine of critical angle, like this. Okay. Then this is what refractive index of air with respect to glass. But what we usually write refractive index of glass with respect to air, right? But we know that refractive index of glass with respect to air is equal to reciprocal of refractive index of air with respect to glass. That's what we write. So from these two, what you can write, refractive index of glass with respect to air can be written as 1 by sin IC, where IC is a critical angle. Right? Then in the same way, by using wavelength also you can write it. Then one more thing. Here by seeing this wavelength, the critical angle is directly proportional to wavelength in that medium. So therefore, critical angle is more for red color, because as red color has a longer wavelength, then violet color has minimum critical angle. Okay. Then let us go for some of the applications of total internal reflection. Number one is mirage formation. Number two is looming. Number three is total reflecting prisms. Number four is optical fibers. Now another one is sparkling of diamonds. Another one also we come across, that is endoscopy. We also use in endoscopy. Now let us see looming. Actually in looming, this is in a cold condition. You can see that when you go to seashore, and from the seashore, if you observe a ship or a boat, it is appeared to be raised up, because here at this position, the surface closer to the water at the sea level. It is denser than this one. So denser than the upper layer. Then what will happen? Light ray travel like this. Okay, it undergo total internal reflection. It undergo total internal reflection like this. But when you see from this one, these light rays are appear to become, see here light rays are coming like this. But these appear to be come from this position. When these are appear to be come from this position, what do you see that the ship or boat is in this position like this. So here wonderfully you can see that when you from not only that you can capture image of that and you feel amazing. This will happen only in during morning or in cold condition, right? Because they are the air or atmosphere which closer to the sea, which cool down very immediately to the air which is far away from the surface of the sea. So during this morning or even evening, you can observe these things. Another important application is mirrors. In case of mirrors, this is in a hot condition when you're traveling in a road. Then you see that there is some water on the surface of the road. But when you go close, go to that position, you will not find any water. This all happen because of total internal reflection. Right? Another important application is optical fiber. Optical fiber. Before going to optical fiber, let me come across to you one thing. Suppose when you go by the side of the road, you might have seen a stone laid with written as OFC. Right? So what is OFC there? That is the optically fiber cable. Just exactly go deep, and if you dig out and if you see that, don't go for that. But if you see that there is a cables which are laid down through a long distance, it is called as optical fiber. Right? These optical fibers can be seen, and even in some shops for ornaments like that, for for decoration purpose, it will be used. Right, but the optical fibers made a very good, wonderful revolution in the field of communication after a discovery of investigation. Sorry, of optical fiber, it made a revolution in telecommunication. Right. So let us see that how this optical fiber works, and we'll go for how it is applied. Right. So optical fiber consists of mainly two things. One is core and another is clouding. So core is a little denser medium. It is just like quartz material. Quartz are a little soft and quartz material, and it is highly transparent. Then, but it is more flexible in nature, right? So another one is it is coated with a thin layer, but whose refractance is lesser than the core, right? Suppose core, if you see here, this is a core, and over that there is a small thin layer will be there. The refractive index of this core should be little greater than this one, thinner one coating. So because of that, you can see here when a light ray enters here, so since and it enter with more than a critical angle, it undergo total internal reflection. When it undergo it, let us see here. Okay. So here you see now. Here I draw normal. This is the angle of incidence. If this angle of incidence is more than critical angle, what will happen? It undergo total internal reflection. Once it undergo total internal reflection, then it go to other surface of this one. Here also it undergo total internal reflection. Here also it undergo total internal reflection. So like this light ray is keep on undergoing number of total internal reflection, and it go to other end of the pipe. So then in this way, and another very important thing is that it can bend through a smaller angle, so that it can even in spite of bending that, this light ray will travel a longer distance, right? So another important thing is the intensity will not be lost when it travel from one end to another end of the cable. And the strength of the signals will not be lost when it travel from one end to another end of the signal, right? So because of this, actually earlier to the invention of this optical fiber, the coaxial cables were using for communication purpose. But it replaced this optical fiber, replaced that coaxial cable. So because of that, Thus, thousands of people can talk each other and send messages and all those things. So even nowadays also we can see the speed of the internet will be increased, can be have as much as possible by using this optical fiber. So because of that, you can send so many signals and you can get the so many signals. Because of that, you can upload the materials and you can download the materials. Right. So this is all possible because of optical fibers. Then after that, one more application is endoscopy. Endoscopy is something that you can see, get the image of inner part of our body. Suppose some problem in your stomach or some other places. What do you do? What the doctors used to do is they put that pipe in through your mouth, and that pipe will go into your body, and it can find any foreign objects or any disorder in your body, so that the same monitor will be, same image will be get in the monitor, right? So with that we can find out the problems in our body, or it will be very useful in diagnostic purpose. Now let us go for the image, obtaining image with an inversion image or a rotating image, right? To get that, you can see here, if you keep an object AB in this manner, in vertical manner like this, if light ray is passing through this reflecting surface and incident on the interface of this glass and air medium, then since the angle of incidence is more than critical angle, it undergo total internal reflection here. And here also in the same way, light ray obtained from A, also it comes here in this manner. Then you get a rotated image. So it is AB is in this manner. Now A dash B dash is in this manner. So in that way, an image is rotated by 90 degree. The same way, now we can see here an inverted image. If an image rotated through 180 degree can be obtained like this. If you keep an object here and it light rays, here you see now B goes like this, and it undergo total internal reflection. Then here one more total internal reflection to go, and it forms the image here. Then the point A image is obtained here like this, and it can go like this. So therefore an image is rotated an image is rotated through 180 degree. So here in the same way, an inverted image can be obtained like this without by using like this. And sometimes suppose a telescope or microscope you are using it, but if you are getting any inverted image, so that time if you are, then to get an erect image, what you can do is, if you pass in this light rays through these kind of devices, then what will happen, you will get an inverted image. Then you see that it's you can see in the same manner. So even if you are using telescopes and all, you can use these things.